Yeah. Good afternoon, everyone. Let me go through the rest of the MEMS devices today. Okay. So yesterday we saw some of the devices in BioMEMS, and then the next one is optical MEMS. Optical MEMS is the technology to control the light. Okay. So for example, like these squares, they are meters, okay? And then the angle of the meters, they are controlled by electrostatic force installed at the bottom. Okay? So it's already like a complex, but when we shine the light, okay, red, green, blue, those light, they will be reflected on the meter, and then we can selectively choose the wavelengths and then combine them with 3 of these meters. Okay. So these are the structures, and then if you see the structure, then there is like a torsion beam and then actuators that is controlled by the semiconductors. And of course, you know, the magic of this MEMS device and fabrication method, that's we can make them as an array. Okay. For example, for this kind of beam projector, it has an array of meters 1,000 by 1,000. So total about 1 million meters, they are controlled at the same time. Okay. And this is the array of meters 3 by 3. So since individual meters should be controlled individually, there is a gap in between. Okay. And then the gap size in the fabrication is limited by 4 micrometer. Okay. And then this 4 micrometer gap is maintained all the way. That's why we can see the grid in the screen. Okay. And the 1,000 by 1,000 meters, 3 of them, they are installed in the projector, and then one of the meter looks like this. Okay. And 1,000 by 1,000 meters are there. Okay. And these days, more of higher degree of freedom of meters, they are fabricated, okay, and then they are being used for the future device. And then this one shows a kind of a movie how a meter can be used. Okay? So meter can be controlled by the micro device. And if you see these small things, that's the COM drive. Okay, we saw the COM drive actuator yesterday. So meter can be controlled. So this large meter is used to reflect very high intensity of laser light. Okay, so we can send a signal or transmit a signal or focus a signal through the meters. And the next topic is radio frequency MEMS. It's RF MEMS. And then if you see your cell phone, then cell phone has this kind of switch. So basic working principle for this device is there is like a RF signal from the outside. Then when this beam is maintains the distance from the bottom of quarter wavelength, then the wavelength is gone. Okay, then switch is off. And with when this switch is kind of completely sagged down, then there is a signal. Okay? So RF signal can be switched on and switched off. Okay? So that's the basic working principle. And then this RF switch has been fabricated in many ways, as you see. And then some of the types, they are installed in your cell phone to receive the signal of a radio frequency. And in microfabrication area, they are approaching to nanoscale devices to fabricate nanostructures. Okay, we call them as like NEMS, nanoscale electromechanical systems. And on the other side, people in science, physics and the chemistry. Also, they are working on a nanoscale particles, but it's not a device. It's kind of material, but it's not a device. So people from the MEMS area, they are approaching the small scale technology. And then, however, the problem of this MEMS device is at this moment, they do not use a advantage of a small scale. Okay, they are just like trying to minimize the size in order to see like what happens, and then they want to develop the process to fabricate nanostructures. Okay. So what we have reviewed at the beginning, we saw what kind of MEMS applications are there, and then we saw a few examples for the scaling issues, and then we learned that surface tension is very dominant in small scale. Okay? So N2 was trapped in a bubble, and also a bug can float on water. And in the MEMS processes, we discussed about the lithography, UV lithography, and then deposition, physical vapor deposition and chemical vapor deposition. And also we discussed about etching method using a gas phase or a wet etching. And also we learned about a thermal oxidation to grow a thermal oxidized film, silicon dioxide film on silicon vapor. Okay? And then those are the kind of basic processes for MEMS. And then we discussed the cantilever fabrication, and in terms of applications, sensors and actuators, they were the first products in MEMS area, and then now a lot of people, they are working on this bio-MEMS because a fabrication is kind of easy. However, there are a lot of unmet needs and demands in this field. That's why a lot of people are working on this area. And optical MEMS is a representative product is the optical meter array. And these days, if you see the network, then originally all the signals were transferred through the wires, but now optical devices and meters, they are used to transmit the signal. The thing is, for this optical signal, is interference is much less, and then we can transmit the signal is much faster. So, for example, like if you want to send a signals with 1 gigabyte per second, then we have to adapt this optical nanoscale technology. Okay, and now this kind of materials have been made through the NSF award and also travel support from the Professor Jae-Hyun. Okay, then I want to go to the nanotechnology. Okay, so when we build up a device, for example, a micro device, then we have to fabricate the structures in micro scale, and then we need an interface to a large scale device. Okay, for instance, I want to build up like a speaker, a small speaker. Then after building it up, you have to package them inside this kind of system, and then it should be wired. Okay, so when the size scale is over like by over 3 orders of magnitude, then the fabrication method is different, and also interface between microscale and macroscale is different. For this nanotechnology, the same thing is applied. The fabrication method is almost like different, and also interface between nanoscale components and then microscale devices or components. That's really challenging. And again, there should be interfaced with nanotechnology. But when we go to this nanotechnology, the structure is getting very simple. Okay, and sometimes we cannot take quite good advantage from this nanotechnology. Okay, for instance, when we make an array of sensors with a 1,000 by 1,000 array, okay, and then if each sensor occupies about 1 micron area, then in the area of 1 millimeter by 1 millimeter, we can fabricate 1 million sensors, right? It's not a small number, right? And even if you go down to this nanoscale, then if we, for example, like make an array of sensors with a 1 nanometer spacing in 1 millimeter by 1 millimeter area, it's like a huge array. Okay? So microscale technology is enough, but there is something new in nanotechnology. Okay? So that's the motivation to study this nanotechnology and then develop a product through the nanotechnology. And you know, there is a science and technology area. In U.S., this nanotechnology has been kind of studied 1990s and 1995, and around 2000, it was kind of boomed up with lots of research funding from agencies. And in terms of nanoscience, that's the study of properties and phenomena at nanoscale. We want to learn what's happening in small scale. Okay? We want to discover the fundamental science. That's the nanoscience. In comparison with that, nanotechnology is a development of materials, devices, and systems based on the understanding of this nanoscience, right? And nanotechnology, terminology itself, it says the scale of a component or device should be smaller than 100 nanometer. Okay? Then why 100 nanometer? Okay? That's the question. So for this 100 nanometer, that's a kind of very weird scale. For instance, we have 2 electrodes. Okay? For example, we can make 2 electrodes through this way. Okay? Now, you know, this distance is like a few centimeters, right? Nothing happening out there. Okay? If we approach this further, like 1 micron, hey, they are very close. Still nothing happening. Okay? If we make it very close, 100 nanometer, then electron starts to transfer from this electrode to the other. Okay? That's called electron tunneling, and also the number of electrons can be controlled because capacitance between 2 electrodes is very small. Like starts to get to below 1 femtofarad, reaching to attofarad. Around a attofarad range, individual electrons can be tunneled and then transported. Okay? Now, when we use semiconductor chips for this kind of computers, we handle about 1 million electrons in one transistor. Okay? But in future, if we are able to control individual electrons, then the size scale of the device will be much smaller. Okay? And then if one electron is passing through the electrode, then we have a specific current. Okay? And then no electrons and no current, then it's another like a digital concept. So those new concepts can be created. Okay? That's the size scale of 100 nanometer. But 100 nanometer is still large. About 10 nanometer or below 10 nanometer, then if we have a really dexterous fabrication method for those scales as an array, then we can truly control the electrons at the level. Okay? So a lot of active research is ongoing among scientists and engineers. And of course, you know, as an engineer, we are trying to make a massive production. Massive production means we wanna have nanoscale devices in 100 millimeter or 200 millimeter wafers. Okay, then we can have devices in terms of number like a trillion devices in like a single wafer. So I would say that's a massive production. And then through the device, you wanna realize nanoscale phenomena. Then that will be really a sensitive sensor, or it will be a very high-speed semiconductor, vice versa. And in terms of information sources, now a lot of journals they are handling the nanotechnology and nanoscience. And then in terms of divisions, it's already like early to define what kind of areas are there. For example, some of the areas it's investigated for 5 years or 10 years, and then if the area does not find the specific applications, then the area is gone. Okay. So, for instance, molecular electronics and nanosensors and actuators and nano-optics and nanomaterial synthesis, nanolithography and spintronics and nanotube-based technology. Now, nanotube is being replaced with graphene and nanobiofusion. This area is for the mainly bio applications. So there are a bunch of areas in the field. And what is a nanometer? Okay? That's the very kind of, it's very hard to get the feeling of scale of nano. Okay, so we live in meter scale, right? We are here, and then when we I ate a kind of guava, yeah, it's a fruit in the morning. It was like in this scale, right? We can grab it, right? It's about like 10 centimeters and those range. And if you go down, then there's like bees, bumblebees and ants. They are in a meter scale. So with our bare eyes, we can see up to about 100 micron. So that's here. So I can see your hairs. Okay. So that's the scale that we can see. And below 100 micron, we have cells, 10 micron. Okay. We cannot see with the individual cells with our bare eyes. However, when we use a light microscope, then we can see those cells. Okay? And with discovery of this light microscope, we started to see the bacteria. Okay? Now, the bacteria for infectious disease, they are being spread out very rapidly. And without this microscope, we couldn't understand what's happening. But with optical microscope, we could see the specific bacteria present for a patient. So the diameter of this bacteria is about 500 nanometers. And if you see this bacteria, it has a tail, right? Tail and small hairs. They are making a roll. Okay, those hairs. One of hair, the diameter is about 100 nanometer, okay? And then it's making some of chemical energy, and then it is converted to a mechanical energy. That's why these bacteria can swim in solution, and also they can get together to make a specific function. And virus, this one has a life, okay? This one has a life. It can generate its own energy, and then it can copy by itself. Okay, it can make next generation. This one, usually virus does not have a life. Okay, in order to copy them, they have to be attached, bound onto the cells. Okay? And then through the cells, they can make another virus, and then it can be spread out. The size of this virus is about 30 to 50 nanometer through 150 nanometer. Okay. Now, if you have a bacteria, then it's easy to detect, relatively. Okay. Virus is very hard. Okay, because it's much smaller. Even this one is about like 10 times smaller. Virus is 10 times smaller than bacteria. In terms of diagnosis, it's not possible. Okay, so if we go down one order of magnitude in terms of scale, then the problem gets very challenging. And from 100 nanometer, we go down one more time. Okay, that's the DNA. Okay? In fact, the width of this DNA is about like 1 nanometer, and then they are kind of twisted. The spiral structure diameter is about a few nanometer to up to like 10 nanometer. So it's a coiled structure, and mechanically, this structure is very interesting because basically we can make any kind of shapes with the DNA, and also it has a lot of information. So that's why we are investigating a lot of this DNA, and still very far away to go down. And you know, if you see the length of this DNA, then in one cell, okay, we have one chromosomal DNA. Its length is about like a few meters, and then its base is about 0.3 nanometer. So it has a huge information source in each cell. Okay? So our body is very complex in nature. And go down one more, then there are small molecules, and then atoms. Okay? In each atom, we can see the electrons. They are kind of rotating around through the orbitals, right? And the thing is, we have like when we have a baby, okay, they have so many cells, and then they are cultured, okay. But sometimes, with some reason, the DNA is not copied very well. Okay, then at an early stage, like age of 15 or before 20, they get a very serious disease. Okay, so these all of those changes, they are coupled with electrons. Okay, so now people in biology and medical science, they are trying to couple the idea of these electrons through the molecules and DNA through the cells. And then again, you know, even we understand the mechanism, how it works. For these cells, it's not directly coupled with our body. Okay? So this multi-scale understanding is really important. And then nanometer belongs to here, and the major observation tool is an electron microscope, because a wavelength of electron microscope is about like a picometer. Okay? So since wavelength is very small, light diffraction is very small, we can see about 1 nanometer, okay, or over. And I found a interesting picture over here. So this is our hand, and then you can see the wrinkles on the skin, okay? And in 1 millimeter scale, we can see the wrinkle very clearly. This is a 100 micrometer scale, and then this is a white blood cell. If we go down, then we can see the white blood cells, and then in the blood cell it has a DNA, okay? And then each individual base is there. We can see at this nanoscale. Okay? Then why this nanoscale is critical in terms of length? Because if you see the x-axis, that's a length. Okay, it starts from a meter, and then millimeter, micrometer, and nanometer. And in terms of energy, okay, it's a joule. And this yellow line, that's the thermal energy. Also, we call it as like a Brownian motion. Okay, so we are not dominated by Brownian motion, right? Even the temperature is increasing, our body is still there. However, if the particle size is getting smaller, then under 10 nanometer, the particle is shaking, okay, and then moving around by this Brownian motion. And thermal energy is about this range, okay? And chemical bondings are there, and then hydrogen bondings are around this range. Of course, you know, if you go over this range, then now like structure is bent by mass, and then also it can be fractured. So this nanoscale range, that's the kind of crossing point of this large scale and then small scale. However, still the surface tension and capillary action is dominant under this scale. But for very precise control, we need to control the Brownian motion and other non-specific and specific binding energies. And in terms of imaging, when we use an optical microscope, it uses wavelengths of all kinds. Then in that case, we can see the particles greater than about 100 nanometer. But it's not such a clear. In order to see a particle very clearly, the particle should be greater than about 5 micron. However, whether there is a particle or not, with a certain shape or size, 100 nanometer, that's the bottom limit. Okay? Of course, you know, if we use a specific wavelengths with a very small wavelengths like 50 nanometer or things, then we can go under this range, but that's not a usual optical microscope. And electron microscope, the wavelength is about 1 picometer. Right? With this wavelength, we can see typically over about 1 nanometer. Okay? The thing is, you know, we have an electron microscope, but with that, it's not easy to see 1 nanometer particles. Okay? It has really complex theories and operation principles. So, in order to use a transmission electron microscope, usually one needs to be trained for about 5 years, and then after 5 more experience, we can take the image of about 1 nanometer. So in order to have the image of this small, like 50 picometer, we need an experience over like 10 years. Okay? Anyway, with the electron microscopes, we can see, visualize individual atoms. And in a smaller scale, there is a critical force called a van der Waals force. Okay? This one is somehow it's kind of a non-specific binding forces. So if you see this graph, this one is a distance between 2 molecules or particles. Okay? This one is distance, and then y-axis, that's the energy. Okay? And then when there are like 2 particles like that, this kind of shape, then they tend to attract each other. Okay, that's the van der Waals force is shown as this one. Okay, so the force is negative. That means they are attractive. Okay, so these 2 particles, they are trying to attract each other. That's the van der Waals energy. And then, you know, if our world is dominated by this van der Waals energy, then when I shake hands with you, then we cannot pull, right? We cannot separate because they will be stick. They will stick each other. So people started to understand what's happening between 2 particles, and then one of them is electrostatic repulsion. Okay? So when particles are getting together like that, there is a similar potential is induced out there. Then, because of the potential in between, they repel. Okay, so that's the electrostatic repulsion as shown. This one, and then actual particle interaction is the combination of this curve and then with this curve. Okay? Then final curve is this one. Okay? Then between two particles, some of distance is maintained over there because it cannot stick each other. But when it is like a far, then it will be attracted. Okay? This distance is within a few nanometers. Of course, you know, if you have a very large object like that, then this force is negligible. But once they are close, like to a few nanometers, then they start to have this kind of a force. This force is called also a Reynolds-Jones potential. Okay? So a lot of research has been done to understand the particle-particle interaction in this scale. And if we get down more, then actually, you know, the understanding of electron behavior is really complex, okay? And then they are always moving, right? So some of research has been done to freeze these electrons at absolute temperature, and then they want to see what's happening out there. Anyway, electrons, as you know, they have a mass property and then wavelength property as a particle and then a wave, respectively. So this kind of understanding helps to make a device in large scale. That's the kind of a fundamental introduction of this nanoscience and nanotechnology, and in terms of a size scale. And in terms of nanotech market, if you say a device, then I think we can talk about these semiconductors. I think that's the major leading motivation to fabricate nanoscale devices. Then, in order to fabricate those devices, we need the equipment and the fabrication tools and lithography. Okay? For instance, you know, I want to build up a facility to fabricate microstructures. Okay? Then we will build up the structure like in this kind of building. Okay? However, if we go down to about 100 nanometer, then we need a spring and damper in the building, okay, in order to observe the energy from the outside, from the ground. Then the building will be isolated, and again, air table will be installed in the building. Okay? If we want to fabricate 10 nanometer structure, then it's another deal. Okay? So they have to make a new building for 10 nanometer fabrication facilities. So it's really kind of time-consuming, and a lot of fund is required to make small devices. Now, according to the market research, they said it's about like $1 trillion per year for the market in this area. However, except the semiconductors, devices in nanotechnology, in terms of electromechanical systems, they are not present yet. In terms of just like a market in nanotechnology, there are a bunch of materials, nanomaterials. For instance, this kind of pad, huge pad, is useful to as an insulation material for thermal heating, or we can control the structure to enhance the transfer of heat. Okay, that's controllable, okay? But it's expensive. Okay? And if you see this surface, then the contact angle is close to about 170 degrees. Okay? It's called hydrophobic. Okay? If you see the surface of Teflon on a frying pan, then contact angle is about like 110, 120, 130. But if you use frequently, then contact angle will be smaller. Okay. So anyway, this hydrophobic property can be changed out there through the surface coating. Okay. If you see an airplane, then surface is coated with a specific material in order to avoid like darts or ice formation or things. So some of research has been done for boat and ships. So they want to make the the surface super hydrophobic on the submarine, then they imagined the friction will be lowered a lot. Okay, it's possible to make such a super hydrophobic surface. The problem was it's too expensive. Okay? But anyway, these kind of new materials and structures they are available. Okay? And adhesive, small materials, they tend to aggregate each other. Right? In terms of nanoscale materials, if you leave it in solution, then they aggregate very quickly. Okay? So that means adhesion will be enhanced a lot. Okay? That's one application. Still, it's a material. And then also, by adding up some of our nanomaterials, the mechanical properties can be enhanced. But you know, the money, price matters, right? Then, in terms of a nano device that we are using, I think you are using the cell phones and those. The critical components, they are made with the pattern size of about 20-30 nanometer these days. Okay? Semiconductor chips, their line width is about 30 nanometer. In case of CPU, like a 27 nanometer, and then they are getting like smaller. Okay? So you like a smaller device, right? Then the semiconductor industries, they will make it smaller. Okay? Then you like it, and market will be created. Then nanotechnology will be improved. Okay? Yeah. Except that, do we have nano devices around, especially electromechanical systems or those moving things? I did not see any of. But in our body, we have a bunch of them. Okay? So let's see. It's a sponge. Okay? It has a small tail. Diameter is about 100 nanometer. It can swim. Okay? Why it swim, and then where does this structure head for, right? How how the direction is induced, right? And also this structure is called a flagellar. Okay? It's shaking this way, and then it's moving forward in a perpendicular direction, right? How about this one? Now it's shaking like this way, and then the fluid motion is going through the same direction, right? So it's called a cilia. Okay? So the small hairs on the cell wall or the like small structures, they can make it like a swim. Okay? I'm going to discuss why kind of this nature have chosen this kind of way to swim. Okay? Because viscosity is very high. Okay? For example, like if you think of saliva, spit, or blood, they are viscous. It's not like water. Okay? Then, if you think of a Reynolds number in such a small scale is below 1. Then, viscosity is really dominant. Okay, compared with the mass. Then, conventional like propellers or other mechanisms that do not work. Okay? They need some of a specific mechanism to swim, or actuating or making a flow in such a small scale. So you know, if you see the motion, then you will see they are vibrating, right? And we can make a similar structure in nanoscale or microscale. Okay? The thing is, physics was completely different in this scale. Okay? Then I'm going to discuss some of those features tomorrow, like mechanics and in terms of fluidics. And today, let's see what kind of methods are available to fabricate nanostructures. And these are the a few methods among various methods. And then now people are trying to find a method that can fabricate like a specific structure. Okay? But if you think of a fabrication method, some of method is a parallel in terms of fabrication. What I mean is, we want to make 1 million devices with a specific method, then I would call that as a parallel. Okay? But with one device, I can fabricate one method, I can fabricate one device, then I would say that's a serial. Okay? So depending on the purpose, we are supposed to choose a right method. Okay? And then one of the cheapest method, that's the micro contact printing. Okay? So even I have like a few $100s, and I can do a micro contact printing at my home. Okay? And then nano imprint lithography is a more improved form of this micro contact printing. Okay? And scanning probe lithography is a lithography tool to use a very small, tiny needle to make the structure. Okay? And electron microscopy is also another tool to use electrons to pattern a polymer layer. Okay? Again, the polymer pattern can be transferred to another metal layer or other layers to fabricate a specific structure. So let's see the methods one by one. Okay? And for this soft lithography, we are using a rubber, okay, elastomer. And it's very simple. So we have an elastomer, and then we need to make a specific shape. Then we need a mold. Okay? Mold means on a silicon wafer, we can use a photoresist as a structure, or this silicon can be patterned to make a specific shape. And then we can pour the polymer. We supply the polymer onto that. This polymer will be cured on the structure. Okay? Then after that, those polymer structure can be made. Okay? Then this polymer structure will be dipped in a solution, okay, having an ink. Okay? Ink means it can be a lot of molecules or solutions containing some of target molecules out there. And then we can just stamp on the surface, then that's it. Okay? So if you see this stamp, okay, then there are a lot of patterns at the bottom. Okay? And after dipping this stamp in a solution, and then if you stamp it, then the pattern will be made on the surface. Okay? So it's very straightforward. However, there can be a lot of problems out there. When we go down to nanoscale, for instance, we have this stamp, okay, with a pattern. And then if you dip this stamp in a solution, then solution will be coated on the surface. Right? And then it will be transferred onto the surface when we place this stamp on the surface, right? So this is the pattern that we want to have. The problem is, now if this side shrinks, then the structure out there, it will be collapsed, okay, by the low stiffness. So large structure is okay, but small structure, usually they can be collapsed like that. Okay? So no patterns out there between, or these two pillars, they can be paired like that. Okay? So it has been studied a lot, the mechanical stability of this method has been studied, and then it turns out that about 300 nanometer, that's the minimum pattern size that can be made with this structure. Anyway, this alkane thiol is called self-assembled monolayer. The stamp can be dipped in this solution, and then when we stamp it on the gold surface, then monolayer will be transferred like that. Okay? Then the area with the gold can be etched selectively. Then, after that, this monolayer will protect the gold layer. The other layers that are not protected will be gone. Okay? That's a selective etching. So we can make this kind of structure with that. So the bright area, that's the gold. So electrons are charged and then bright. And the other area was etched by selective etching method. Okay. It's called micro contact printing. Elastomer, the materials, polymer is very cheap, like $100. Then they will give you like 4 liters, okay, very big, big box. And then also the mold, it's about like $100. So we can purchase it with a specific pattern. And then we need a solution also that's very cheap, so we can make this kind of patterns with a very low cost. The advantage is this stamp. It can be flexible and bent and then rolled. So in that way, the patterns can be continuously copied onto the surface, and then this kind of three-dimensional structures can be made using this micro contact printing. So 1995, around this time, this kind of technology was very popular, and still this structure is used for microfluidics. It's very straightforward to fabricate this kind of structures. And in terms of biosensors, it's very easy to transfer the specific recognition molecules through the micro contact printing. Okay? That's why this micro contact printing is very popular. And then size scale is a 300 nanometer. It's not that small, but in terms of biosensors and this purpose, it's good, small enough to fabricate the structures. And the next one is nano imprint lithography. Okay? Nano imprint lithography, it's a kind of smaller size in terms of soft lithography. So it's similar to a micro contact printing, but this one is a kind of more precise handling in terms of pressure and temperature and also mold. So mold, usually it's fabricated by electron beam lithography. So the small pattern can be as small as 2 or 3 nanometers in terms of size. The major steps for this nano imprint lithography is 3 steps. First of all, we need to make a mold. Okay? Mold usually is very hard material on silicon. Okay? So we can make an order to make this kind of mold in a wafer. Then in a wafer, we want to have a pattern size of 100 nanometer. Then it's about like $4,000 or $5,000. It's expensive, more expensive than micro contact printing because of the small size. Then those small features will be made by electron beam lithography. Then we have a stamp, but at this time it's a hard stamp. It's not a soft stamp. And then imprinting, that's happening. We can use a mold, and then a mold will be placed on a polymer layer, and then with the heat and then pressure, the polymer can be patterned. Okay? And post-processing is to clean up the surface with the oxygen. So some of polymer will not be transported on the surface. Then those debris will be removed using these post-processing steps. So this is the fabrication steps as a whole. Okay, we have a silicon wafer. and then it's coated with a photoresist, and then exposed with electron beams. Okay, electron beam is very tiny, so electron beam will be focused and then exposed on this polymer. Then those broken polymer chains will be removed in solvent. And then after that, we can coat chrome and nickel by physical vapor deposition. Then we will see those small patterns, and then in solvent, all of those structure, they can be removed at the same time. Then we have all these small structures. Using this metal structure, we can do the gas phase etching. Then the anisotropic etching process will make this kind of structure. Okay? Then this is the mold. Okay? If we do not have this kind of device, like equipment, then we can purchase that. Okay? Let's see. This is the mold. Okay, cross patterns. Okay? In terms of size, this size is about like 200 nanometer, and the width 100 nanometer and 200 nanometer. So the whole length is about 500 nanometers. Okay, one of a crossbar structure, it doesn't do anything, but as an array, it's doing something. Okay, let's see what can happen. So using a silicon mold, okay, mold is there. It can be stamped on the surface, but at this time, the surface is controlled by in order to create uniform pressure, because it's a small scale. So if the pressure is not even, then the structure on the right side and the left side will be different, right? So pressure is maintained by hydrostatic pressure or whatever, and then temperature will be increased about 155 C with a pressure of this much. Okay? So 155 is the temperature greater than the glass transition temperature. So polymer will be plastic over this temperature, and then at this high temperature, the polymer layer will be like a viscous fluid. Then all the fluid will be transported into these small gaps. Right? Then the remaining pattern is left on the surface. And then after that, if it's cooled down, and then the silicon mask mold will be separated from the resist. Okay? So this is the shape that we can have. So we have 2 layers of polymer, and then with the pressure and heating, those materials will be moved, okay, transported. Then we have some of the debris out there. With the oxygen plasma, we can clean up the surface, and then we can coat a gold material on top by physical vapor deposition, and then we can remove all other polymers in solvent. Then the leftover is these structures that we would like to have. Okay? So I'd like to mention there can be a potential problem for this. These are our steps. So the critical physics happening in here is that we need this type of hard mold, okay? And then it will press onto a polymer layer, okay, on another hard material silicon. It will be pressed, then you will pressurize the polymer layer like that. Then this material, right, should be transported to this area, right? So depending on the pattern, for example, like we have a pattern like that. okay, or pattern depending on the width. This kind of pattern, or the reverse one is this kind of things. Okay. This pattern can transport the material. However, the materials that is kind of moved, squeezed, that the space to be squeezed is very limited for this case, right? In comparison with that, this structure is very narrow. Okay, so the polymer material underneath will be transported very well, right? So this kind of nano imprinted lithography has some of a limitation in terms of the shapes and features. Okay, so those should be investigated further to have a high yield process. Anyway. If you see this crossbar structure, then all the materials will be transported from this crossbar structure. Okay, so it's close to this shape, not this shape. So it's easier to fabricate. Okay. When we have an array of this crossbar structure, and when we transmit a light, it will remove specific wavelengths. Okay? So it's kind of a frequency selective surface that can be made through the structure. And we have two lines. One is from the E-beam lithography, I think this one, and then the other is a nano imprint lithography pattern. Then interestingly, the frequency that is observed by the surface is different, right? It's a little like shifted, which means the shape of the structure is kind of distorted during the fabrication. Okay? But it was a work in 2000 that was quite much improved. And then the equipment to fabricate this kind of structure is about like $500,000. So if we are interested in an array of small structures, then this device can be used. And for this case, they want to make a very small structure using a silicon material. So they use the nano imprinted lithography to fabricate this kind of patterns. And at the same time, at an early stage, these lines, structures have been made as a waveguide. And also, around same time, like small structures, the width is about like 100 nanometer. They will fabricate as an array. But you see a lot of defects on the structure, okay? Because it was an early stage. And then this person, Steve Cho, basically he invented this approach. And then what he envisioned at the time was 4 by 4 centimeter area. They can make a bunch of these structures. Then 45 gigabits can be generated. Like in a CD, is a much more compact form of a storage device can be made. That was the device he envisioned. But the yield still is not such a kind of good. But yield is good over 100 nanometer. But if we want to fabricate a 10 nanometer structure, then as an array, it doesn't work very well. And then, in more recent years, those small structures were fabricated for sensors. So silicon wafers were patterned with a method, and then it's kind of a relatively new tools for nano imprinted lithography, and then that was used to fabricate about 100 nanometer width patterns. Okay. This is almost like a state of the art of nano imprinted lithography. And the next tool is scanning, probe microscopy. Scanning probe means it's using a very small tiny tips. Then we call them, it's kind of a general terminology to mention a small tips. Okay? Small tips is really useful in this small scale. For instance, let's say we have this small tip. Diameter, for instance, is 10 nanometer. Okay? If we approach this tip onto a surface, okay, then if we apply an electric potential, then electron path that's confined within this range. Okay. Then, with the application of the voltage, for instance, we can modify the surface. Okay. Silicon surface will be silicon oxide, for instance, or some of surfaces they can be reversed. Okay. Or let's say this tip is is made of very tough material. Then we can scratch the surface to make a pattern on this soft substrate. Okay. So we can make a pattern like that, and we can scratch that. So, and also we can transfer specific chemicals through the small tip. Then also we can etch the surface. Right? So if you have a scanning probe microscope, then we can do a lot of interesting things. So this is the early version of the device, and then it's coupled with an optical microscope, and then small tip is installed in the device. And this is a structure of a typical scanning probe microscope. So we have a small cantilever, and then at the cantilever, a very sharp tip is fabricated. So fabrication itself is done by a microfabrication approach, and then one tip is typically about $5 to $10. Okay, it's not that expensive. And then the motion of the tip is detected by a laser. Okay? So detector, it has 4 segments. So each 4 segments has a photodetector. So its motion of the tip cantilever is detected by the laser, and also that's coupled with piezo, okay? Piezo tube. So XYZ control that can be controlled by the piezo, and also motors, and then detection is done by the laser. So the height difference that can be measured up to like a sub-nanometer, okay, using this laser, and then also the height can be controlled by a nanometer range. Okay? So what it does is it can measure the force, van der Waals force, between the tip and the surface. So it can be used to image the surface, or it can modify the surface, like this case, by applying an electric potential or whatever. Or it can scratch the surface through the tips, or it can chemically modify the surface. This is one of our typical structures, and then this one is a tip fabricated by micro machining. Okay? It's not that hard to fabricate this kind of a sharp tip. Tip diameter typically is about 20 to 30 nanometer by microfabrication. And then in order to have a higher resolution, we can attach a nanotubes at the end of this silicon tip. Okay? This tip is about $5. This tip is about $100. Okay? So by attaching a tip, we can increase the resolution, but fabrication is much more challenging than this one. That's why it's very expensive. And if you see the resonance frequency, then this cantilever resonance frequency is about 300 kilohertz. Okay, and then cantilever length is 100 micron, and then tip diameter is about a 20 nanometer. Then if you see this structure, these individuals, they are cantilevers. What I mean is they have, for example, 100 cantilevers, then they can make 100 patterns at the same time. Okay? Basically, with one tip, we can make one pattern. It was serial, but now it can be used to make patterns in parallel, right? Even though it's parallel, it's very slow, right? Because we can make 100 patterns at one time. So it's very hard to make 1 billion patterns, right? With the structure. But still, the method is being improved. So if you see the structure, the fabrication method, then using the tip, we can transfer the electrons, then that will be exposed into this polymer layer. Then a hardened layer will be left, and then the other layer will be etched out. Using this one as a mask, then we can etch out more of the silicon. Then these are the silicon structures that are fabricated using this method. And this one is another kind of a branch method of SPM lithography. So actually, for this method, my friend he invented this method. At the beginning, he in his PhD he worked on a atomic force microscope. It was 1980s through the 1990s. Okay? And he studied how to operate this AFM, okay, and then how to scan the surface. That was his PhD dissertation. And he spent about 10 years in physics department of Purdue. And then he came up with some of device, okay, and then it's almost done. Then suddenly, like Binning group in IBM Zurich, they published the result before my friend, and then he got a Nobel Prize, but my friend, no one remembers him. Instead, he invented this approach. He learned this AFM, studied for about 20 years, and he was a real expert. And then it was a very hot, humid summer during in Chicago. Okay? And then he operated this AFM in his lab, and then found that this tip is kind of stuck on the surface. Okay? And then he changed the tip with a new one. Looks like something wrong. So and then tried to operate again, but it was again stuck after like a 20 or 30 minutes operation. Okay? And then what he kind of assumed, hypothesized, was this one. So solution, the small moistures, when this tip is approaching to the surface, small moistures, they will be attracted by the capillary action between this AFM tip and the surface. Then that will form a meniscus. Okay? Then, due to this capillary action, the solution will be liquid will be formed. Then that will increase the friction on the tip. So that's why he sees some of the stiction of the tip on the surface. In order to prove that, he transferred some of liquid molecules on the surface with the tip. Okay? For example, he dipped the tip into the solution and then moved on the surface. He stayed for 1 minute, and then he sees this kind of small drop. Okay? And then when the time was increased, he could see larger drop. Evidently, some of the solution is transferred onto the surface through this capillary. Okay? And then when he moved the tips on a horizontal and a vertical way, he could draw this kind of pattern. Okay? And the method was further developed to deliver the fluid through the small tips. Okay? So solution is stored in this micro chamber. and then there is a very thin film here, and then through the small nanoscale channel, the solution is delivered, and then it was transferred onto the surface. Okay? That's in that way he can pattern the surface, okay? And this kind of cantilever was fabricated, and then a lot of patterns can be made at the same time. Now, you know, they are trying to find the application of this, and then one of the application is encryption. Okay? For example, the kind of money, paper money, that's easily copied, right? So they want to know like whether it's a real money or fake. Then now some people, group people, they are trying to find a way to make the encryption on the paper money with this kind of tools. And then similar tools will also be made to scan the surface. And then if the nanoscale pattern can be detected with this device, then that's real. Otherwise, it's a fake. So those kind of encryption is being studied through the method. And this is a kind of a movie showing how the interaction is working. This is a nanoscale surface, crystal surface is an array of atoms, and then the tip is detecting the surface morphology. So I showed you how the van der Waals interaction is working. Now you know the attraction force that's detected by measuring the van der Waals interaction out there, and also that's controlled by the optical laser and also piezo together. Okay. So we scan the surface in one way, and then they can be put together, assembled to have a whole morphology on the surface. So this tool can be used to scan the surface at the same time pattern the surface. Okay? So that's the SPM lithography. And then even a one atom can be moved by the force. Okay? So IBM group, they demonstrated that they can make some of Chinese character atom through that way. Okay? So in future, very precise patterning can be made, atomic level patterning can be made through the device, but of course, you know, it's very slow. Okay? Yeah. In order to move a atom, we need to spend about a few hours, then it can be moved like a few nanometers. Okay? So it's very time-consuming procedure, but anyway, it's meaningful in that a nanoscale patterning can be made. And electron microscope, I think this is the approach that I'd like to introduce at the final. So in electron microscope, the major difference between electron microscope and optical microscopes is optical microscope that's using a photon, okay, light as a medium, but electron microscope that's using an electron to see the surface. That's the major difference. And then when we transmit the electrons through a surface, then if we see the diffracted pattern or transmitted pattern of electrons, then that's a transmission electron microscope. In comparison with that, if we see the elastic or inelastic reflection of electrons on the surface, that's a scanning electron microscope. So in case of a transmission electron microscope, we can see through the materials, but if the material is very thick, like 50 nanometer or 100 nanometer, then of course electrons cannot penetrate, then we cannot see that. In this case, it's a single wall carbon nanotubes, so you will see the tiny walls. Okay? Diameter of a single carbon nanotube is about a 1 nanometer, and then wall thickness is a 0.3 nanometer. So we can see through those bundles of nanomaterials And then in the right case, it's a small particles. That's a ion catalyst to grow a nanotubes. And compared with the transmission electron microscope, scanning electron microscope is to see the electrons that is reflected from the surface. So these are the nanotubes, and then resolution of this SEM is much poorer than transmission electron microscope, but the preparation of a sample is less demanding, because if you have to select sample, then we can see the structure. You know, at an early stage of my study, I with mistake, by mistake, I stamped my finger onto a substrate, and then I saw those fingerprint under a electron microscope. It was really surprising. You will see like something is crawling in the fingerprints and things. So after that, I'm like washing my hands 100 times in a day. Yeah. So using the microscope, of course, you know, also we can see the diffraction of X-ray. Then we can see what kind of elements are there. Okay, ions or chloride, silicon, and other materials are there. So that's very useful to study the elements. And the electron beams, technically they can make the pattern as small as about 5 nanometer. Okay, so we can pattern the polymer surface like that, or those polymer patterns can be transferred onto a metal layer. And this is a 250 nanometer gold ellipse. You know, it's easy to make the surface, but you know, if you see the width, then it's about less than 1 micron, right? If you want to pattern 100 millimeter by 100 millimeter wafer, then it takes about 10 hours, because it's serial process. The electron beam should draw all the patterns, but you know, it's being improved. Okay, so very recent electron microscope, it costs about like a few $1 million. They can make these patterns within like 10 hours. That's a state of the art. And also, in one way, people are trying to use electron microscope to do testing of nanomaterials. Okay. For example, like we have this nanowires. The property of this nanowire, you think it will be similar to the bulk material or not, right? Those questions were raised, and then actual test was done. So Young's modulus can be coupled with the resonance frequency in high vacuum, or like a by tension test, we can see the Young's modulus of the materials, and then the tools to make those are like welding or other necessary assembly tools. They were developed together. So let's see a movie that was done. So it's about 500 micron wire, and then we are zooming in using a scanning electron microscope, right? Then you will see a lot of like blurs and then pits, right? Now this size scale is about this one is about 1 micron, okay? And then getting down to about 20 or 30 nanometer. Okay? This scale is about 20 nanometer. Okay? So that's the scanning electron microscope. And this one is SEM environment to see the growth of a nanotube. Okay? So this is a wall of a nanotube, and then in a very high temperature and specific gas environment, they found that this catalyst, based on this catalyst, nanotube is growing. However, if you see the shape, then it's not such straight, right? Then there's a lot of defects that are created during the growth of these nanotubes. You can see that. And this one is experiment being done in scanning electron microscope. So XYZ stage, piezo stage, that's used to move this nanowire, and this is kind of tweezer. So it's trying to hold it using electrostatic force or whatever. Yeah. So now the screen that we see is two-dimensional, okay, and versus the motion is controlled by three-dimensional. Right? So my friend worked on this kind of project. He learned the skill for about 3 to 4 years, and then it took about like a few hours to hold a single nanowire. Okay? Then using this nanowire, he can do a lot of tests to find out the material property. Okay? And here is a kind of summary. So most of lithography method. Okay? Top one is ultraviolet UV lithography that was used to microfabrication. And then pattern was about 2 micron. The good thing was the patterns can be made in parallel, because if you use a mask, then the patterns can be transferred at the same time. And then deep UV is a smaller wavelength, so we can make smaller patterns. And extreme UV is very popular these days, and resolution is getting down to about 30 nanometer, 20 nanometer in the scale. And then still the pattern is transferred through the mask, so it's a parallel. Electron beam lithography, we gotta use focused electron beams to pattern it, so it's a serial method, and resolution is very high, 10 nanometer, but it's very slow, right? So SPM, scanning probe microscope, I introduced a scanning tunneling microscope, and then depend lithography to use a capillary action. So those methods were serial, but they become a parallel by using an array of small tips. And insult lithography, micro contact printing, and nano imprint lithography, they were introduced. And for this micro contact printing, it was like a single rubber, so we can scan the solution onto the surface. The good thing was the cost for the lithography is very low. So, for example, in U.S., about 300 to 500 groups in one university, they are working on this micro contact printing to make a microfluidic device. And nano imprint lithography is to pattern a polymer using a hard silicon mold. So the process is parallel, and then they argue that they can make a 10 nanometer, but with a very small area. Okay? In a large scale, they can make about 100 nanometer. So there are a lot of like tricky things, but depending on the method, there are various limitations and also opportunities out there. And X-ray, I did not discuss about this X-ray. In the early stage of this technology, accelerators to accelerate electrons, those big, huge equipment have been used to pattern it, but now this kind of technology is too expensive. For example, in order to run a accelerometer in our lab, have to spend about the initiation cost was about like $40,000 or something like that. So, and then also the method itself is not such safe, okay, because X-ray is being used. So this method is not popular these days. And then nano patterning method, these methods are available. And in terms of bio applications, these two methods are very popular. So those are the nanolithography and then imaging. Do you have any questions?
Você vai ficar acanhado, não. Qualquer qualquer coisa, ele também vai estar, ele está aí na engenharia mecânica, se quiserem bater um papo com ele, é só passar lá.
Yeah, any questions, okay.